Hi, I'm Dale Ron.
Hi, I'm Steven Moore.
My name is Yuri Liu.
My name is Alex.
Hi, my name is Ben Windsor, and I'm the lead designer here at the Madison College.
Hey team, I know it's coming up on boat naming time here. We have a couple of options, but Ben had one, a Greek inventor who created wings. What do we think about Daedalus?
Based on the E1 class racebird, the Daedalus features a twin-foil monohull design, prioritizing a narrow beam and minimal wetted surface area once on foil. With little to no existing schematics available, as E1 is a new sport in just its second season, the hull and foil geometry were developed by measuring a scale model using calipers and radius gauges, then painstakingly recreating it in SolidWorks over approximately 200 hours. The model was then integrated into a custom 6 degrees of freedom simulation for performance analysis.
That was a brief overview of our final design, but that wasn't where we started initially. Originally, we were considering a twin-hull catamaran due to stability concerns from previous years. To predict resistance of these displacement hulls, we did an implementation of the hull Troutman method in GNU Octave. We quickly realized from this model and other related research that hull speed limitations meant that we would not be able to go nearly as fast as we wanted to, so we moved on to considering a planning hull. For predicting resistance of planning hulls, we did an implementation of Savitsky's method, again in GNU Octave. We did some simple sensitivity analyses on how each of the input parameters would affect the model output, but before we could come up with any concrete designs, we decided to try a more ambitious approach and go with a hydrofoiling design. Since we could not find any empirical methods readily available for resistance predictions for a hydrofoiling vessel, much effort was spent on trying to learn CFD. As students competing in the PEP competition, we did have access to commercial software, but it was cautioned against starting with them since they are often not as transparent and can easily produce bad results. To that end, we tried to start from the foundations with fluid mechanics, then aerodynamics, then trying our best through CFD theory. The software we ended up using was OpenFoam, and many unrelated test cases were done to try to master the software. We ended up spending around 2 months on this before realizing there was still too much to learn and it was unlikely for us to get useful results out of it. The stage we were stuck on was generating a good computational mesh of our geometry. Our boat being a hydrofoil craft meant that it was quite unique and had a large range in relevant dimensions. The smallest core length was around 6 centimeters, which meant that for good lift and drag predictions, the laminar to turbulent transition had to be modeled. This meant we had to use a 4-equation Langtree and Mentor variant of the K omega SST turbulence model, but to fully utilize the high fidelity of this model, we had to ensure the non-dimensional wall distance y plus was less than 1. That, however, required either an unreasonable high mesh resolution for the computational power we had access to, or an unreasonable amount of inflation layers that the mesh generator for OpenFoam Snappy Hex Mesh struggled to make. After realizing this, we decided to abandon the CFD approach and to use the readily available airfoil data online instead. This sacrificed accuracy, but was the best we could do with the time remaining. We started first by creating a 0 degrees of freedom steady-state model based on force equilibrium. At each velocity, a certain amount of lift must be produced to counteract weight. In this model, the lift coefficient was allowed to vary as a proxy for angle of attack effects. After finding that, the induced drag formula combined with a fixed baseline drag coefficient was used to find the amount of drag that had to be balanced by thrust at that given velocity. Propulsion was modeled with the Wageningen and B-series polynomial fits for thrust and torque coefficients, and the RPM required to generate the required thrust was found at each velocity through optimization. With the RPM found, we can then find the torque and through the ideal motor equation, get the required input voltage and current draw. This combined with the expected runtime allowed us to get a first estimate on our required battery capacity. We quickly realized that this model had too many limitations and unaccounted dynamics to be a good predictor, and we decided to move on to a 1 degree of freedom model where the height above the free surface, or Z, was allowed to vary. In this 1 degree of freedom model, foils were modeled individually, each having their own lift and drag coefficients from airfoils of similar shapes. We had tried to export our foil shapes and simulate them in Flow5 with boundary element methods, but none of our attempts converged and we lacked the expertise or time to troubleshoot this. Instead of a varying bulk lift coefficient, there would be a certain amount of lift generated at each velocity, and whatever was left was taken up by buoyant forces. To model this, we needed the submerged volume at each given submerged depth. We took the CAD model of the hull and took booleans of it at various depths and did a quadratic fit through the origin for submerged hull volume at any given depth. This data combined with an estimated final mass and a waterline height that seemed reasonable meant that we could work out the displacement needed and what our final hull size would be. It ended up being around 1.7 meters, multiplied by a safety factor of 1.25, we ended up at the length between perpendiculars to be around 2.13 meters. The submerged volume data was then used to find the Z position of the craft in the pre-foiling regime where the hull still provided buoyant forces. After takeoff in the foiling regime, lift produced by the foils alone was enough to support the weight of the craft. The foils start to surface and decrease their lifting area. Submergence was calculated with the Z coordinates at the intersections of the panels, and the submerged lifting area was then linearly interpolated. Propulsion was once again modeled with B-series polynomial fits, but instead of optimization, it was noticed that the thrust coefficient Kt was a perfect cubic of the avance coefficient J. This allowed us to rearrange one analytical expression for J for any given required thrust, and that meant the computational cost of each analysis was significantly reduced. We then did lots of manual optimization, trying out different propellers with different parameters. It was found that at our target velocity of 15 meters per second, we needed a high pitch-over diameter ratio, and also a high blade area ratio propeller to produce large amounts of thrust at low speeds. Since the propellers were optimized to be efficient at high speeds, they were rather inefficient at low speeds, and most critically, the takeoff speed where drag was greatest. We briefly considered adding a second motor and propeller right under the hull that could be optimized for takeoff speeds and hopefully allow the entire system to be more efficient. This idea was ultimately abandoned due to the uncertainty of modeling surface-piercing propellers and the added complexity of powering another motor. Similar to zero DOF, power requirements were calculated with torque requirements through the ideal motor equations. The final result ended up being around 525 watt-hours. We decided to order two 666 watt-hour batteries and wire them in series for the necessary voltage. This should in theory provide more than enough power even with them being rapidly discharged. The motor was also picked to have a continuous power output rating that exceeded the power requirements produced by this model. And although this was a massive improvement to the last model, there were still many limitations, the main one being that this was a steady-state model based on only force equilibrium and not moment equilibrium. It was felt that the only way to capture these dynamics was by including more degrees of freedom, leading to us developing the 6 degrees of freedom model. The nonlinear 6 degrees of freedom dynamic model was heavily modified from the RCAM Research Civil Aircraft model with the help of a paper titled Hydrofoil Craft Dynamics and a realistic C, including automatic control. The panels were once again modeled individually, this time with a much more robust way of calculating submergence using quarter-chord locations in the world space to account for varying roll and pitch. Foil lift and drag were modeled with coefficients in the stability frame similar to aerospace models. One problem we had was that when the craft was nearly stationary, the angle of attack and side slip varied wildly from -90 to 90 degrees. This meant that the lift and drag coefficients no longer stayed in the linear and quadratic regions respectively. We came up with arbitrary blending functions that we tuned to resemble airflow data of similar profile shapes. These were sampled and stored in a lookup table and interpolated in 6DOF. A similar problem was encountered when trying to model propulsion. Since we wanted to model reverse and braking, this meant that the avance coefficient J would go out of bounds for the B-series polynomial fits. We switched to a 4-quadrant propeller model with Fourier coefficients instead to model the 4 different operating regimes. There were only data for a few select B-series propellers that were readily available online, and from those few we selected one with a blade area ratio of 0.7 and a pitch diameter ratio of 1.4. Propeller rotation speed was again solved through optimization offline at any given input voltage and speed, and again stored in a 2D lookup table and interpolated in 6DOF. For treatment of the hull, volume center and area centers were now needed for where the buoyant and hydrodynamic lift and viscous forces would act through. These were sampled at various Boolean waterline heights, each with a sweep through pitch from -45 to 45 degrees and through roll from -60 to 60 degrees. It happened to be rather computationally expensive to sample these quantities, so they were sampled on an irregular grid at first, densely near their normal operating latitudes, near zero pitch and roll, and sparsely at the extreme ends of each scale. The data was then interpolated on a regular grid for easy access and quality check through a custom plotly visualization. This multi-dimensional array was stored and then trilinearly interpolated in 6DOF. The equations of motions were that of 6DOF rigid bodies with rotation tracked with Euler angles instead of quaternions for simplicity, and since gimbal lock was not going to be an issue. The model was implemented in Python with an object-oriented style and slightly optimized with profiling and with NumPy just-in-time compilation. NumPy was used to handle matrix and vector operations, SciPy for integration, and WebSockets and async I/O for communicating with the front-end visualizer in JavaScript. A separate script started a local server and used Pygang to communicate with the controller and for throttle and steering input. JavaScript was chosen for the front end due to its 3D visualization capabilities with Three.js. 6DOF was used to get important force and moment outputs to help guide design decisions. Test runs could be completed in 6DOF and with telemetry logged. It was found that only around 1/3 of the battery capacity was needed to complete the race. Multiple propeller diameters were tried, and after examining each of their current draws, it was found that a reasonable diameter would be around 12 to 14 centimeters. We had planned to do more stability analysis through linearization about trim points, but those were omitted once again due to time constraints. 6-off also allowed us to modify wing geometries and see their effects on the craft performance after there were concerns with manufacturability of the smaller wing panels. The electronics consists of a main circuit with two 6-cell 30 amp hour batteries wired in series for a nominal voltage of 44.4 and a peak of 50.4. This achieves high voltage for minimal power loss, but stays below the competition limits of 55 volts. The circuit was controlled by a 300 amp contactor, which was energized by an auxiliary circuit powered by a 3S battery. This auxiliary circuit also powered cooling pumps for the ESC, bilge pumps in case of significant water ingress, and the linear actuator for rudder actuation and steering. The auxiliary circuit was controlled through a relay that was energized by a low power control circuit consisting of a radio module and the microcontroller. We chose the Teensy 1.4 as our microcontroller due to its computational power and onboard SD card for data logging capabilities. For our radio module, we selected the XP XR900, which had enough performance and was much more cost-friendly than the other alternatives. For our antenna, simple link budget calculations were conducted. Care was taken to use a two-ray ground reflection path loss model instead of free space path loss due to us operating in near proximity to the water surface, which reflects and distorts signals. Omnidirectional antennas with isotropic gain of 2.2 dBi was chosen for both the ground station and receiver, and the control program on the ground station side was done similarly to 6-off with Python, starting a local server and interfacing with the joystick HOTAS controller, and XP through the Digi XP Python library. It broadcasts control and telemetry information through WebSockets to another JavaScript front-end interface. We had identified 3 main risks and 1 minor risk. Firstly, we were worried about loss of communications and/or onboard hardware failure, leading to an uncontrolled USV. We try to mitigate this through an intelligent receiver that performs onboard safety checks. If the link to the ground station was lost for more than 1 second, throttle and steering would be cut to 0. The ESC also provides active data feedback, so if the link to the ESC was lost for more than 1 second, main power would be cut through the contactor. The contactor also has an auxiliary circuit that provides information on whether the coils are energized or not, and if it is commanded to release but fails to do so after 1 second, the auxiliary power relay would be cut. If at any point we notice off-nominal performance, the ground station has the ability to cut main and auxiliary power. If all the above measures fail, there is a physical e-stop that cuts power that energizes the auxiliary circuit relay. If this also fails, there is a physical 300 amp turn switch wired in series with the main circuit. With all these measures in place, it is felt that safe operations is guaranteed. A second risk we identified was thermal runaway. Basic thermodynamic calculations were done for the ESC, and a cooling pump with enough volumetric flow rate was selected to keep the ESC below 60 degrees Celsius. The third risk identified was an inadequate steering system that was too sluggish or not powerful enough to overcome hydrodynamic forces. Expected forces and torques, actuation speed, and ranges required for reasonable maneuverability was found through 6-off. Calculations were done to ensure the linear actuator chosen has specifications that met desired performance. The final minor risk was flooding. Much care was taken to watertight seal the entire hull. If somehow significant amounts of water do get in the hull, there is a bilge pump that should ensure we will not sink. There are also air bladders required by the rules that ensure the craft stays positively buoyant even in the case of complete flooding.
The inward curving foil arms improve stability and load distribution while providing balanced lift and roll control. A rear T-foil with twin rudders adds pitch stability and control authority during operation, and the Flipski 85165 19.5 kilowatt motor is mounted between the rudder plates, turning with the rudder via a transom-mounted linear actuator, matching the full-scale Racebird configuration. As the system reaches takeoff speed, lift is generated by the hydrofoil profiles, raising the hull approximately 20 centimeters above the waterline. This transition significantly reduces drag and energy consumption. Similar hydrofoil systems have demonstrated reductions of up to 80% under optimal conditions. Trim is controlled through ballast placement just ahead of the center of gravity, combined with pilot throttle input. The hull itself is a 2.5mm marine-grade MMA thermoformed monohull. With strength, stability, and safety as primary design drivers, a full internal structural frame was designed, using 3/16-inch 6061 T6 aluminum, including a continuous wing-to-wing connection and reinforced transom for the rear foil and motor. The structure itself was laser cut in pieces, then TIG welded using 4043 filler to ensure longitudinal and torsional rigidity. A 3D printed cap completes the system, providing sealed access to internal components. The hydrofoil wings and rear stabilizer are 3D printed in PET-G filament, featuring 25mm wall sections and a 3mm gyroid infill. Components were produced in multiple sections on bamboo H2D printers. Each assembly is reinforced with 3/16-inch steel dowels, then all bonded together using Sikaflex 291 marine epoxy. Once installed through the hull and secured to a carbon fiber composite brace plate and central mounting structure, each wing assembly weighs individually about 8.5 pounds. While this may not represent the lightest possible configuration, it prioritizes reliability and safety, things that were really important to us.
Hey Ben, this is Steven. I just wanted to call and double check to make sure everybody had all their gloves and glasses and everything. Since we're starting the production this week.
Our goal for this year is not only performance, but proof of concept, to demonstrate that the Daedalus can successfully achieve sustained hydrofoil flight. Future teams will have the opportunity to refine the design through weight reduction, efficiency improvements, and extended testing. But for this competition, our objective was simply to raise the standard and push beyond conventional solutions. As mechanical designers and engineers, we set out to challenge expectations, and this is the result.